Hey guys, what's up? Eddie Aho here with KissAnalog.com. Alright, so today we're going to talk about another type of switch mode power supply. Just for vocabulary, you see the acronym SMPS, so switch mode power supply. Well, now, I'm not talking about buck converters or boost converters. I sometimes hear, I kind of laugh a little bit, but not to give any of you guys grief, but like let's say a guy doing digital design, he might get some voltages, use some buck converters and boost converters, and regulate some voltages for the different outputs he or she needs, and they consider themselves a power supply guy because they create their own switching regulators. But that's kind of like back in the day when they used to use linear regulators. And if they just dropped down linear regulators, they probably wouldn't have called themselves a power supply engineer. But with switchers, they're like, oh, see, I'm just switching power supply. But guys, really a switching power supply is a power supply, where you take power from some source and you isolate the power for your secondaries. So you have a transformer in there where you're isolating the voltage from one side to the other side, like all these instruments have, right? They're taking AC voltage, converting it to DC, and then going to a transformer and providing secondary voltages. And those secondary voltages, the return paths, grounds, are all isolated from the primary side. And we do that for safety, for one, especially when dealing with AC stuff, and also for power integrity, to keep your signals, the noise off these return paths, like if you're powering fans, let's say motors, but you're also going to be powering some RF circuitry or some digital circuitry. You don't want those return paths, those ground paths, being connected and sharing the noise, and that kind of thing, right? So you can go through a power supply, a real actual switching power supply where you have isolated outputs. Now, once somebody's designed a power supply with a transformer in it, where they have isolation, now they're starting to really, that's where you start really getting into power design. Well, two of the most common ways to do that is flyback converters. That's a really common one. Television, especially when they had CRTs, they need high voltage. Flybacks are really common. They still are, because they take a few less parts and they can be a little less expensive. Forward converters is another really common way, okay? Well, I don't want to say recent years now, because it's been a couple of decades now where active clamp forward converters or even active clamp flyback converters have hit the scene. And it took me, honestly, a little bit to kind of catch on. And here, let me show you why. And by the way, I have this board from Texas Instruments. We're going to come over to the bench. I'm going to show you this thing close up. We're going to look at some signals so I can actually show you what it looks like, okay? But here, let me just show you on my little whiteboard here. Okay, I just want to kind of show you what a forward converter is and the difference between a forward and an active clamp. Now, a forward converter, you have your voltage over here. Maybe you got it from a solar panel. Maybe you got it from the AC voltage. You went to a bridge rectifier, bulk capacitor, and now you got your DC voltage. Now you're going to convert that to a high frequency waveform so you can make the transformer a lot smaller than you could with the 60 hertz through a linear transformer, right? That's the whole idea of the switchers and the isolation. And so here's a forward converter. When you turn on the switch and you energize this transformer, you're energizing the secondary output at the same time. So that's a forward converter, okay? And it's an actual transformer versus a flyback converter is a little bit different. It's more of a inductor versus a transformer, and when the transistor turns off, that's when the energy is transferred, so that's why it's called a flyback. This is a forward converter, okay? That's the difference. So we use the dot nomenclature to kind of show polarity. So let's say when this transistor is on, the top of the transformer, that dot is positive. The secondary side is positive, and this diode turns on and transfers energy across a transformer, okay? When this transistor turns off, then this inductor doesn't want to stop current flow instantly, right? You get a big kickback voltage. So what you do is you use this reset winding, also known as a tertiary winding, to your third winding. Now you can have multiple windings on the secondary. You can have multiple windings on your primary. You might want to create a 12 volt on your primary side to power your PWM chip. Well, but anyway, this tertiary winding, you need at least 3 windings for the transformer. And the way it's polarized is the winding is connected with the diode, and what it does is that diode's reverse polarity when the transistor's on. You get plus, plus, and you get plus down here at the return side of this winding. So the diode's reverse polarity. It's not turned on. Now this guy turns off. These windings instantly, this primary winding instantly transfers the voltage switches instantly because it tries to force its current to continue going through the way it was. When that happens, this tertiary winding is positive up here. Now this diode's forward biased, and now it can sink energy from the transformer back into where it came from. It's kind of trying to conserve it, same time getting a path for the transformer to discharge that energy. So what happens is, imagine this part, this is a switching node right here, so we're looking at it within the oscilloscope. Imagine right here the transistor's on, it's pulled down to 0, transistor turns off, it lets it fly up. Now what actually happens, there's some ringing, there's some noise because of parasitic capacitance and the MOSFET, also leakage inductance in the transformer, things aren't coupled perfectly, so you get a little bit of ringing going on, and then it clamps, and then what happens is this voltage right here where it's flat, let's just say you had 50 volts here. Well, when this transistor turns off, now it's open circuit, so you get 50 volts here. But you also have 50 volts across the winding that you had before, and it's switched polarity, so now you have 100 volts. So you got a 2x voltage factor when it first turns off. Now, once this magnetic has transferred energy from, all the energy's been transferred, then it starts to just kind of ringing. It's just, it's out of energy. It's just kind of flipping around. Well, and then the transistor turns on, pulls back down, you start another cycle. Okay, so you get a little bit of noise here. You can use snubbers. You can slow down the turn-off cycle or something like that. You can do different things to try to get rid of some of this noise that could cause EMI issues. And this could cause EMI issues too, this uncontrolled kind of ringing that happens. Once the thing runs out of energy, you got now more parasitic, usually lower frequency, and it just kind of like, oh, I'm just flapping in the breeze now. Okay? Well, the active clamp came along. I thought, the vendors would say, hey, you can get rid of that tertiary winding. I'm like, it's no big deal. It doesn't really add a lot of cost. I'm not afraid of designing transformers, so that doesn't really save me a lot. Why else would I do it? And they're like, they didn't really have any good answers. So I looked into it more myself, did some simulations, and I realized something that was counterintuitive. I thought this was a natural way to kind of fly back energy, kind of let the transformer reset back to 0, let the magnetic field just, naturally turn on the tertiary winding and then dissipate energy and go away. And I thought adding an active device was going to cause more EMI issues. Now you have to have a timing thing. The timing can't be better than a natural thing, right? But it actually can, because you can foresee what's going to happen in the future, and you can do something about it with timing. So instead of having to wait for the diode to get enough voltage to charge to turn on and things to start flowing, you can jump ahead of the curve and turn things on and get it all ready. You can do things like that. And also, as energy dissipates, you don't have to, like, oh, the diode's running out of energy, and now it's going to start kind of having an issue right there at the turn-off period. With this, you can pull it down and keep it down until you're ready to turn this transistor on again, which keeps this voltage at 0, so when this guy turns on, he has 0 voltage switching. So it kind of helps a softer switch. So what happens is the square wave, when it releases, instead of having this ringing, it doesn't have that. Now it's got a bigger capacitor to dampen that out completely, totally override any parasitic capacitance. The other thing it can do is the capacitor is big enough where it charges up and it kind of averages all this energy. So you end up with kind of this rounded square wave. Okay? So much better for EMI. more efficient because you don't have the switching losses. You don't need a snubber. So just, you know, the active clamp for converters become like a really big thing. Really favored, you know, topology. Okay, let's come over here and take a look in real life. Now this is, by the way, this is using Texas Instruments UCC 2897 chip. And this chip has been a great chip. It's got some really nice features. Its performance is really top notch. So let's come over here and take a look. But first, let's take a quick look at the data sheet, and I'll show you a schematic of this board so you can know what you're going to see when we come over here, okay? Okay guys, this is a schematic. Now let me just kind of cover the big parts and then we'll kind of zero in on things, okay? So up here in the top left we have our input voltage. Now in this case it's 1836 volts. You know, this could be a high voltage like off a bridge rectifier off AC input, right? So it could be 180 or 220 volts. But in this case it's lower voltage, so let's say it's nominally 24 volt battery is what it looks like it's set up for. Okay, then we have our PWM controller right here, this UCC 2897 chip. This is our active clamp forward converter control chip, and it's operating 250 kilohertz down here. You can see that. Now over here in the middle we see our transformer. This is transferring the power from the primary to the secondary, and the output is top right, 5 volts 5 amps, and that's coming off this LC filter right here. Okay, we're going to talk about how it gets there, but it's off this LC filter. That's our output. Okay, now our feedback loops, we have two. One is the obvious one, voltage feedback, because we're regulating the voltage. So it's right here, bottom right corner, V out, comes through this voltage divider, and it comes in and it feeds this TL431, which in this case you can kind of think of it as like an op amp. This is one reference pin, and up here's another. And so if this voltage is anything less than TL431L, so that's a 1.24 volt reference. So if it's above or below, if it's above, it's going to pull current through this guy trying to pull this down, and if it's below, it's going to not pull current. So if it's pulling current through here, then it's coming from this path right here, which is this resistor and this LED part of the optocoupler, the feedback loop. So we have a current path coming from the V out through resistor diode to this TL431, and that's how it tries to regulate that voltage at this pin at 1.24 volts. And this capacitor is a feedback from this pin to this pin. Okay, so these diodes and these resistors and capacitors, they kind of set up a soft start and stuff. We can go over this stuff in another video. This stuff is just kind of help the thing run better during startup. Okay, so basically we have our transformer for isolation from primary to secondary. We have our optocoupler for the isolation from our feedback voltage from this side to that side. So if we follow this path for our feedback, see this resistor right here pulls up to VREF 5 volts. So we have a pull up of 5 volts, but this pin can go, you know, if this transistor is turning on, it's pulling this down to ground, and if it's turned off, then it lets it go up to 5 volts. And over here is the voltage feedback. So that's coming from this sense right here. So that's how we control our duty cycle. Okay, the other feedback path we have is through this primary winding. We have, when this FET right here, this is a control FET. So through the primary winding, there's a dot. That dot is positive polarity when this FET turns on, this control FET. Okay, and then there's the current pulses through this resistor, and we get current sense feedback right here, and that comes in over here in the top of this chip U1. Okay, so the current sense comes in, has a RC filter right here between those two parts, comes in here, and so pulse by pulse we're monitoring the current. Okay, So when this turns on, we get positive on this winding, comes through here. We have another winding, we get positive on this one, and it comes to this diode, and this forms our VDD voltage. And this is the voltage that we feed back to our chip over here to run our PWM chip off our transformer. So it makes it more efficient than running it off of 1836 volts. It can run off, say, 12 volts. Okay? So that's more efficient to do it that way. So on our chip over here, we have our VDD right here in the lower left corner that we supply voltage to our chip. Okay? So going back to the transformer, when we get that pulse, it creates our VDD, but it also creates voltage on the secondary. We get our dots up here, so it puts a positive out here. See, the positive just flows through the inductor. There's our LC. Now we should have a FET up here, right, or a diode, but instead it's on the low side, so it's on the ground side. So come over to this ground, and the schematic's just drawn, so it's kind of hard to see. For now, ignore all this circuitry on the gate of this FET, and ignore all this circuitry on the gate of this FET. Just look at the two FETs. So current comes through the inductor, to our load, back to this ground pin, and then over here comes back through this FET to the bottom of the winding. That's our power loop, okay? That's the loop that's controlling this. Now this capacitor and this R right here, that's a snubber across the winding. All right, so now the FET turns off over here. So let's see what happens. Current's flowing through the inductor, it turns off. So instead of going that way, it charges up the capacitor and goes to our active clamp transistor, which has been driven through this capacitor over here, the aux circuit, okay? So that's our active clamp circuit coming into action. Well, at the same time it happens, this one gets reverse polarity, so we don't have any current flowing there. So over here, what happens is these FETs are self-driven. See the voltage right here? It says V secondary 2. That means that's connected right here. So they could have just drawn the line to make it easy to see, but anyway. So that's connected right here. Okay, and then we also got V secondary 1 right here. So that comes up to this side, okay? So when this was positive, we have positive voltage there, positive here, turns on this FET, which is in the return path, and closes our loop, okay? Now when this FET turns off, everything's reversed. So now we got positive down here, it goes VSEC 2. So this one's turned off now because that's negative up here. VSEC 1 is negative, and VSEC 2 turns on positive, so it comes over and turns on this FET. So now this FET allows this inductor here to continue the current flow through this path. So that's how that works. So there's our voltage loop. One thing I didn't point out was this capacitor down here. This capacitor is from primary ground to secondary ground. And now obviously you can see the ground symbol. This is the wrong ground symbol, by the way, guys. They're showing earth ground. That is wrong, wrong, wrong. So stop doing that, okay? We got to stop doing that. This ground symbol should be another diamond like that saying S ground for secondary ground. This is primary ground. So that's just wrong, okay? All right, so here is the test report for the PMP22509. That's this eval card we're going to take a look at. So I'll just show you real fast. Yep, there we go. You're going to see it again. I'll show you on the bench. There's the back side of the card. Here's the efficiency curves. You can see, it's very efficient through. Here's the load across the bottom, output current, and you can see the different input voltages right here, 18, 24, and 36. 24 is a nominal, so the optimal. So that's where you get the optimal efficiency, and it happens right here in the middle of the load curve, right around 3 amps. You're getting 92+%. That's pretty darn good. Now low load, obviously that's where you get the worst efficiency. You're not burning very much power, so that's kind of okay,
But it's bad because you need a certain amount of power just to run everything. So even though you're not supplying current to the load, you're running things on the input. So that's why the efficiency is always bad right here. This is just kind of a reverse way to look at it. This is how much power you lose on the board. Okay, here's some thermal images. This is kind of interesting using thermal cameras. By the way, I have a nice thermal camera, but they've come out with the better one, and I'll put the link down below if you want to buy a thermal camera. Use the link, please. Now here's wave shapes. We're going to see if we can capture the same wave shapes on the bench, okay? This is the switching node. So this is the when the voltage is on the FET, and when the FET's turned on, it's pulled down to 0. This is, by the way, this is 18 volts in, okay, 5 amps out. Now here's what it looks like with 36 volts in. So the on time is shorter. See the time when it's pulled down to 0? It's shorter because you have higher voltage. You don't need to send as much voltage to the output, so it's on for a lower amount of time. Now here's the 18 volt thing again. Now the yellow one is showing the reset FET. So it's on when this guy's off. So it's just the opposite. And here's the 36 volt condition. So you can see the same kind of thing. And you can see there's dead time in between these edges. Now here's a startup with no load. That's just a soft start, what we call it. And here's with the full load startup. So just a little bit different. There's a little bit of inrush right here in the very beginning, but then it comes up here. And here's our output ripple. So we'll see if we get the same kind of thing. I'm not going to be pulling quite 5 amps, so it'll look a little different, but yeah, there's the output ripple. It's fairly clean, actually. And here's a loop response on the feedback, on the gain. So just kind of shows it crosses over at about 2, 3, 4, 5.5 kilohertz right about here. And there's some transients, like when the load changes from, let's see, it changes from 1 amp to 4 amps, and it pulls it down, the output down a little bit, and then when it changes again, when it drops back down to low load, it overshoots a little bit and comes back down. But it's well behaved because you don't see ringing after. So that's what you want to see. You want to see it overshoot, and then you want to see it come down nice and even. If the loop's a little bit too fast, you'll be seeing some ringing here. If it's a little too slow, you'll see this decay very slowly. But this looks pretty good.
All right, so here is our board, and what I want to start off showing is a transformer. This is an isolation barrier here. You can see the copper here. Now the black terminal here, this is return path on the output. This is a positive side of this one on the input side over here. You can see the ceramic capacitors, and here's the return side on this one. So you got a big old plane here for return copper, positive here. On the output, you got a return plane here and a positive plane here. So you can see input power comes in through these ceramics, and there's a little bulk over here. But we have our transformer, and then these are the synchronous rectifiers on the output, the FETs here, with our LC filter on the output, ceramics, and a bulk. Up here you can see a U2, which is the opto isolator, and that's crossing the boundary as well. And I'll flip it over, and then on this side you can see the boundary again. A few components on the output side, and we can see the input side. This is our controller chip, and we have our little inductor for our, well, this is our bootstrap winding coming back, providing power to the controller. And here's our control FET and our reset FET. Okay, here's a kind of a zoomed in picture. Alright, so I've got the setup. I got input power from my power supply coming in here, and I've got the scope probe times 10 coupled right here, and they have these nice test points. On the output, they have some test points. I have a differential probe because our grounds are isolated. I'm keeping the isolation using a differential probe. And I have my, here we got the EV blog meter looking at the voltage here on the output, and also this 8 ohm load. And it'll be a 5 volt. So yeah, let's go ahead and we're here. Let me show you the power supply. I'll run this guy up and we'll see this guy turn on. Okay, here maybe I can get both in the picture. Okay, so right here, this is channel 2. It's set for 1 volt per division. That's our output, so we'll see it jump up 1, 2, 3, 4, 5, jump up to here. And channel 3 is our input. It's 5 volts per division. And right now I got 5 volts, so we'll see it 10, 15, about 18 volts, the output should jump up. Okay, so I'm at 5 volts here. I'm going to go ahead and start increasing that. You can see on the scope we're 10 volts, or 15, sorry. And right there, yeah, the output just jumped up. So right around 18 volts. And then if I drop it down around 16 volts, it turns off. Let's see. Yeah, 17.7 volts, maybe it turns on. And 16.7 or something turns off. So there's some hysteresis, so that's good. You don't want it sitting there toggling on and off all the time. So I'll set this right at 20 volts, so it's just on. Okay, there we go. We got 20 volts, about 0.16 amps. And look at that, 3.2 watts. And with an 8 ohm load, we have about 3.12 watts on the output. That's about 97-98% efficiency. Pretty nice. Alright, so I'm going to AC couple the output. So that way we can zoom in on the ripple. We'll bring it up here. Okay, and then we will get the frequency. Okay, there we go. We can see some ripple. And you know what? The other thing is, so we can use this 20 meg. That's typical to read ripple. But we can also do this low pass and get even a cleaner signal. Now maybe 30 kilohertz is too low, maybe. There's a 20 meg, but we could go to, yeah, look how clean you can make it by just filtering off some of that high frequency noise. Okay, we'll just go, well, okay, I've got 4 meg. We'll just leave it there for now. Okay, there's the output ripple, and let's zoom in a little bit more if we can. And also I'm going to move the trigger to the output so we can trigger on that better. There we go. Alright, and you know what, let's get the cursors. Okay, the cursor's right here showing about 4 volts, or 40 millivolts right there. And down here, we're showing about 13 millivolts RMS. So, yeah, it looks pretty good. I mean, pretty low ripple, 5 volt output. Alright, and just adding the frequency for channel 2. So now we got that measurement. It's 250, I don't know, it's kind of bounced around, 270 kilohertz maybe, switching frequency. Okay, now what I'm going to do is I'm going to move the scope probe over to the switching node. Okay, and we'll have to bring that down so we can see it. There we go. And I'll freeze it just so you can get a nice picture of it. So there you go. The transistor's on. It lets go. And if you, okay, this is 10 volts per division. So it's 10, 20, 30, 40, 50, about 55 volts it jumps up to. And then it's nice and flat, and it gets pulled back down and it's flat. So we've got 20 volts in. So that's here. So twice that would be 40, but it's going up a little bit higher than that, right? It's almost 60 volts even. But you can see how clean the waveform is. We don't have a lot of ringing like we would on a normal Ford converter. There's a little bit of ringing right down here at the bottom where it first turns on, it pulls down, it does ring just a little bit. Okay, so now I've moved the probe to the output. So now both probes are on the output. This is the switching node at the input of the inductor. And so you can see how that's happening. When the transformer gets energy, we pop up and then we drop down. But you can see the energy here on the secondary side. It's 2, 4, 6, 8, about 8 volts, and it's a volt second thing. So the average, since it's 5 volts out, the duty cycle, if we take the duty cycle with the 8 volts, we'll get 5 volts. Hey guys, so what do you think? Active clamp Ford converters are really cool, and actually fairly easy to design relative to other converters, and they perform awesomely. You can get a couple hundred watts easy out of them. So yeah, I highly recommend using active clamp Ford converters. If you guys want to see some more wave shapes on this one, like this output synchronous rectification, that's just a bonus that this one has. You don't have to have that with Ford converters, but low voltage, it's nice to have that. I've got another active clamp Ford converter. I think it's a 100 watt, or maybe it's a 200 watt. I think it might be a 200 watt board. We can look at that one too and look at some signals. So yeah, let me know what you guys like. 2 thumbs up to my patrons. Really appreciate you guys, and I appreciate all you guys watching the videos. And by the way, Stronghold, I'm going to put the links down below. I don't know if you guys ever watched Mr. Ballin. Man, I get hooked on his videos. But he talked about, he was a SEAL, Navy SEAL, and he talks about a guy that he worked with that went into the kind of the private sector, taking care of people, helping people in trouble, and this is their organization that they're raising money. So highly recommend checking it out, and if you can, donate a little money to them. Now these links don't do anything for me, so I'm not like trying to sell you anything. I just think it's a really cool thing, so I bought a shirt, and I'm actually trying to help out a little bit. I don't have much, trying to run my own channel, but anyway, I do support these guys, and so I wanted to wear a shirt to just pass on that message. Links down below to the video where he talks about the guy and how come he started this. It's an amazing story. I highly recommend watching that video. So, alright, thanks guys. We'll talk to you later.